Hi, I'm Abida. Today I'm going to talk about K-Medoids on graphs with structural rounding. So first of all, what is K-Medoids? Specifically, I'm talking about K-Medoids on graphs. K-Medoids is where we select K-Medoids or exemplars from the set of vertices that every other vertex in the graph is going to be assigned to that particular medoid. And this is going to end up partitioning the graph into K clusters. Every cluster has a medoid, and every node is going to be assigned to the cluster that has the closest medoid in it. The best optimal partition or optimal set of medoids is given when we minimize some objective function. The objective function that we're probably going to use is going to be the sum of distances over the over all the vertices to each of their medoids. So let's go back to this and think about why I care about K-Medoids and what the issue is exactly. Well, K-Medoids, the way that I just described to you, is an NP-hard problem. And so you're losing one of two things when you try to solve for K-Medoids. You either lose the fact, you either get a fast answer, but it's not going to be very good, or you get a good answer, or it's going to take a really long time. And we want to get better solutions that don't take too long of a time. Like, is there a good balance here? And so we're going to look for solution methods that give us approximate solutions for K-Medoids when the graphs are particularly difficult to work with. And we want to create solution methods, but then there are a lot of graphs out there and a lot of different graph classes, and these particular methods may not work very well on them. So we're going to do a bit of give and take here, where we find a method that we think will work pretty well, and then we're going to figure out ways to break it. Okay, so like I described, we want to think about how well does K-Medoids actually work. If you have a nice graph to begin with, say a tree, or other examples, then running the machine learning algorithm does not take too long. You get a pretty good answer, and it's fast. There are different ways to run K-Medoids. One example would be using Lloyd's algorithm, but you can also run and get an exact solution to K-Medoids on this problem, and it doesn't take too long because, well, your graph is a tree. Well, if you don't have a nice structured graph, like it's not a tree, or it doesn't have low tree width, or some other nice property, well, running that same algorithm or running any algorithm on it, we don't have one where we're going to get a good solution that's going to be fast. So it's either going to be bad or it's going to take a long time. Maybe though there is a nice in-between there. Like maybe the graph isn't like really that horrible, it's really just a tree, but it has a few, I don't know, extra vertices, extra edges. Maybe you need to contract an edge, maybe you need to add some vertices, maybe you need to add some edges, and you could do that. You can just sort of clip away the bad part of the graph. And that graph that you get is just going to be a nice tree plus some parts, some edit set that overall is really not that bad to work with. So if there is a way to do this where we take our slightly less than friendly graph and we just clip away at it to get a good tree and get the bad parts, then there might be a way to apply K-Medoids to the problem and get a solution on the nice part, and then somehow extend our solution to the bad parts of the graph. And we get a fast algorithm, and we get a good, probably not as good, but a good solution. So the thing I described working on the spider part of the graph is how are we going to apply our edited solution, our solution to the edited graph back to the original graph. And there are many ways to do structural rounding. So structural rounding is just a word that describes all the different ways that you could apply the solution to the original graph. So for example, you could get K-Medoids on the original graph, and then when you add you could get K-Medoids on a graph from which you've removed some vertices. When you add those vertices back in, you could just assign those vertices to the closest center, and that would be it. Or if you have removed R vertices, you might want to do K minus R centers on the edited graph, and then when you add those R vertices back in, you just say they're their own center. So there's like a couple of different ways to do this, probably way more than I've listed here, and those are different ways that you can get a good solution. So maybe that's good. We have a good solution for the edited graph, and we have some structural rounding method. But maybe unediting the graph and applying our solution to the original graph could be really bad. So the challenge here is that we don't really know how badly our solutions are going to behave when we convert the solution back. So for a given structural rounding method, we don't know that. So maybe we need to think about what kinds of bounds we want to put on the types of edits and how much we're going to be allowed to edit the graph. And we're going to put bounds on it. We're going to create new structural rounding methods that are better and stronger and faster. I don't know. But then we're going to do the opposite of that. We're going to discover these strategies, and then we're going to figure out how to break these strategies. We're going to find graphs for which these structural rounding methods fail. And hopefully at the end we'll have a really good structural rounding method that works for most of the graphs that we're concerned with in whatever domain that we're interested in, or the graphs that we tend to get. And maybe, I don't know, we could even have good statistical bounds on how well these algorithms are going to behave. So here are some other methods of doing structural rounding. I described the first one, which is assigning the edited vertices to the nearest cluster. You could do that, and then you could apply your usual Lloyd's algorithm to do a constant number of assignment and update steps. Or you could say, instead of a constant number of update steps, you could have an arbitrary number of assignment and update steps. But even with these methods, we are going to come up with an ugly graph that doesn't work. And then we're going to say, okay, maybe like a stronger structural rounding method will work. And then we make them nastier still. So this is what we're going to keep doing. And hopefully, in the end, discover a good structural rounding method and discover some good bounds on how well our structural rounding methods can do. And that is the goal of the project. There are a couple of problem variations that we can also think about, but really those are just going to be little tangents to the main part of the problem which I described. And that's at the end.